Thank you very much. It's a great pleasure for me to be here on this first activity of the new Mathematical Institute in Ukraine. So I want to start the story, so the title is going to have to do something with zeta of S and its zeros. But actually I want to connect the lecture course that Marina gave to this story, and that would require some time, and hopefully by the end of the talk, whatever that time may be, this story will actually appear. But if not, I at least formulate the result, but then we'll see how much time I'll have to actually discuss it. So I want to kind of fulfill my quota for actually proving something during my talk, and I will kind of fill a gap in what Marina was talking about. So I want to start with the theorem of Kohn and Elkis. That she formulated, and I'll give the proof, which is almost a complete proof, but it's not without all of the details. So the theorem of Kohn and Elkis starts with some Schwarz function. So let f be a Schwarz function, which means it's smooth, it's rapidly decaying at infinity, and all of its derivatives are like that. And well, you start not just with arbitrary things, but you have some conditions, and they're given in the form of inequalities. So you want your function to be non-negative for x bigger than
non-negative?
Non-positive. Well, I said the right thing. I wrote the right thing. I said the wrong thing. So non-positive outside the ball of radius are not. And you want it to be the Fourier transform to be non-negative for all psi. And at the moment, it doesn't really matter what the normalization for Fourier transform you pick, because it's essentially just saying the function is positive definite. But for the rest of the, for the rest of the proof, actually, it will be important. So I'll just write it here. And here it's actually the Lebesgue measure, but I'll often write just dx because I'm lazy. And so there were two sets of inequalities and normalization. So I'll add it to the list of conditions. So whenever you have such a function, the conclusion was then the center density of any, I'll write this. So radius over two sphere packings. So then center density of any R naught over two sphere packing is at most 1. Okay. And so I hope this is clear. So I just mean I'm packing balls of radius R naught over 2, which is the same kind of notation. Well, maybe it's a little bit different what Marina was using. And I want to actually prove this theorem because there was some condition that Marina wrote down without actually explaining. So in certain dimensions, there are these so-called magical functions. And then not only they satisfy these inequalities, but they satisfy a lot of other things. And I want to explain where those other things come from. So I want to prove this.
Question.
Yes.
Is there a lattice in the picture, or is just any R0?
Not at the moment. So it's just any, so Marina formulated it for any periodic sphere packing, but actually any sphere packing has densities bounded by the periodic one. So if you bound the density for periodic packings, you bound it for everything. So here at the moment there is no lattice. But actually it's a good point. So immediately I don't want to prove the general statement. I'll just prove this statement for lattices. So let's just say we have a lattice. So let the sphere packing be given by a lattice. Well, and I will only prove it for this case, but the proof actually is very easy to adapt to arbitrary periodic packings, and then you get it for everything. And so what we're trying to prove, so what do we want? What do we know? If lambda is a packing of poles of radius r0 over 2, it means that the minimal non-zero vector in the lattice is at least of length r0. And we want to conclude that the center density of that lattice, which would be just 1 over the covolume of the lattice, so 1 divided by the volume of the fundamental region, so we want this to be bounded by 1, well, which is a little bit awkward, so I'll just say we want to prove that the covolume is at least 1. So in each fundamental region we have exactly 1 sphere, kind of, and so the covolume of the lattice should be at least 1 for this condition to hold, and that's exactly what it is. So I'll just prove this statement, that if for a lattice the minimum is at least this, then the covolume is bounded from below by 1. And the proof is one line, but if you've never seen it before, it looks silly, but bear with me. So I start with the number 1, which is the value of our test, this magic test function f at 0. Then I add infinitely many values to that. Basically, I take all the values of this function at all points in the lattice lambda. So by this condition here, all of the values that I've added were non-positive, which means I get an inequality in this direction. And so the non-trivial and kind of the most important part of the proof is I apply Poisson summation and maybe let me formulate it here in general. So for any lattice lambda in Rd, yes, we have the following formula, which is called the Poisson summation formula. And let me do that with shifts. So there's something else here which I don't want to discuss too much at the moment. So there's something called the dual lattice to lambda, which is something that's always defined for any lattice. But basically there's some other lattice over which you can replace summation of your function over the original lattice by summation of the Fourier transform over the dual lattice. Psi times v. Okay, so this is the general form of Poisson summation formula. I want to apply it just for my lattice lambda, which means I get this.
X is equal to C.
Sorry?
X is equal to C.
X is it? Oh, yeah, you're right. Thank you. So I want to apply this formula in the special case when the shift v here is 0, which means I don't have any kind of phases here. And the summation goes over the dual lattice, which I haven't defined, but I mean, it doesn't even matter because I will apply in a moment another inequality which is very kind of rough. So I'll throw out every term which is not the origin. And I can do that by the second condition of the theorem. So it's non-negative everywhere, so I don't lose. Well, I mean, maybe I lose something, but at least I don't lose much. And in fact, since the normalization was that I started with 1 for both Fourier transform and the function, at the end, maybe I haven't. So this notation here that I've used is the same. So this is co-volume of lambda. I mean, I just used 2 sets of notation. And in fact, if you look at the beginning of the line and the end of the line, it's exactly what I wanted to prove. So that's the whole proof for the case when your sphere packing is given by a single lattice. But in fact, if you just now assume that it's any periodic packing, and you write a similar line, it's a little bit longer, where you write the sum over all translates that define your periodic packing, and then you apply again Poisson summation, you get a virtually identical proof that now works for every periodic packing. And in particular, so why I wanted to give this proof? Because it actually tells you what should happen for this to become an identity. So there was this conjecture, which now has been proven, again by Kohn and Elkis. Well, okay, it has been proven in almost all the cases of interest. So for D1, 2, 8, and 24, this bound is tight in the sense that it gives the optimal sphere packing density. And well, it has been done in these dimensions, and 2 remains somewhat of a mystery. But so what should happen if you look at the proof, it actually tells you more than just the bound. It tells you exactly when this bound is an identity. And so let's look at the case of 8 dimensions, which is a theorem that Marina has proved. And I'll try to explain a little bit where these kind of strange vanishing conditions came from. So, since the notation maybe was like this. So lambda, the lattice corresponding to the E8 root system, I mean, there's a classical description, but there's also a very explicit description. So you take all integral or half integral vectors, but you want all of your coordinates to be either integers or half integers at the same time, such that the sum of coordinates is an even number. So one can check quite directly that this is, well, it's a lattice. That much is easy. It is even and unimodular. And it's also self-dual, which is a corollary of the previous 2 properties. And self-duality just means that this dual lattice I've defined before is equal to the original lattice. And so what do these words mean? So unimodular means the co-volume is 1, and even, I mean, this is a definition. This is a definition. And this is equivalent to all squares of norms to being even integers. And so all of these properties are very easy to verify directly, so just by hand, or you can use some other properties of lattices that you know. And so, well, what's kind of important for the whole story is, well, this set of properties in dimension 8 actually defines the object lambda E8 uniquely. And in fact, if this were not the case, any other lattice with these properties would be also the best packing. So, yeah. So let's look at this line. But now instead of lambda, I will write lambda of E8. And so if f is an optimal, well, the terminology never kind of stuck with me, but a magic function, we'll use it just once today. then a lot of other things should happen for this to be an identity. And, well, we should have this, and we should have this for all of the points which we so bravely threw out of the equation. So for all x in lambda, and here as well for all except at 0, x in the dual lattice except at 0. But since I said that the lattice is self-dual, I'll just write it again. And there's another property which is, it's kind of much harder to appreciate it at the beginning. So for the E8 lattice, the set of conditions here is just a collection of concentric spheres. So i.e. f of square root 2 S7 0 and f of square root 4 S7 0 and so on. And this happens for all square roots of even integers. So let me write it in a normal way. So f of x equal square root 2n for every psi.
So f is radial now?
That's the kind of funny part because, well, I didn't say anything about radial here. And here, well, since the properties of the lattice, I didn't really, I mean, I can rotate it by any way, in any way I want. And the proof there should still give the same answer. So it means that even if your function is not radial, the vanishing will happen on all of the concentric spheres. So I don't know if that point was completely transparent, but so because I started with an arbitrary lattice like that, any rotation of that would work equally well. And that's one of the reasons why you don't expect a natural non-radial function to be a magic function, because even if it's non-radial, it would still have to have vanishing sets which consist of spheres. And in fact, well, it's now almost a theorem, but modulo some details. So it's not, doesn't help. Okay, so what I wanted to say is, well, we have already vanishing for all concentric spheres. And then if you do the plots that Marina did, so if you plot here x squared and here f, I think she used E8 of x, then this is some function that behaves like this. And if you do the plot for the Fourier transform E8x, well, you get the same type of vanishing. And so, well, here, so that's another kind of subtle point, which is crucial, absolutely crucial. So we have just vanishing to first order by the proof. But we also have the original conditions which are erased, which were the inequalities. And in fact, at almost all the points, they force second order vanishing. So, because your function should be non-positive everywhere starting from square root 2, you actually get vanishing also for the derivative. And for the Fourier transform, it happens everywhere. So, kind of, if you believed Kwon and Elke's conjecture, and that's what, well, certainly Marina did, you would have to find not only a function satisfying some inequalities, which are, well, they're tight, but actually there's an infinite collection of identities that they also satisfy. And it's somehow, the key to the construction is actually to concentrate on how to satisfy all of these identities. And then the inequalities come later as a computation. So we have, and from now on, let's switch. I'll switch kind of to, I'll abuse notation now. So f is going to be radial, and I'll write f of t for t a non-negative number. This would just be the common value of f well, for any x with a radius, and hopefully you won't mind this too much. So we have a collection of numbers that are forced by the condition of being optimal for the sphere packing, for this linear programming bound of Kohn-Delkis. And so the
equal to 0.
Sorry?
These are equal to 0.
Yeah. Well, okay, that's true. I'll just say it in words. So the conditions are actually, they're almost all vanishing. But let's just imagine a more general situation. And in fact, there's a different problem which absolutely requires that general situation. What if they're not necessarily 0, but they're just a given thing? And we want to find a function which has these values. So since from the very beginning, kind of as a simplifying assumption, I said the function should be Schwarz, these numbers can't be arbitrary because they have to decay, and they have to decay super polynomially. But otherwise, it's very hard to come up with any other restrictions on this set of numbers. If I added 0 and to this list of values, you would also have some identities which are the classical Poisson summation formula and some generalizations of that. But in fact, if you remove all of those and all of the clever combinations of those, and you try to play around with this problem, it's very hard to imagine any other abstractions. And so, and in fact, there are no other abstractions, which is this interpolation formula that Marina kind of outlined. And this is a starting point, actually, of my talk. So, and the theorem is, well, for any, and I'll only formulate it for d dimensions, for any radial Schwarz function on R8, we have the following explicit, well, it's not explicit at the moment, but it will actually be explicit. There is a linear formula which actually does this reconstruction from these values. With absolute convergence, uniform convergence, any type of thing you want, as long as you work with Schwarz functions, with A, N, B, N, some explicit functions. And so in principle, once you have this formula, it tells you exactly, well, one function that might work for the sphere packing problem. So this gives...
These are universal functions independent of f?
Yeah, AN, yeah, so at the beginning you might think, and in fact that's what we believed, that maybe there's several ways of doing that. But in fact the situation is completely rigid. There's exactly one formula of this kind, with this summation restriction, and all of the coefficients are uniquely determined, and there's no way to. So the coefficients are definitely uniquely determined, no matter what space of functions you're trying to work with. The only question is whether it requires strictly the functions to be Schwarz, or maybe for some bigger class. These coefficients are completely unique. And well, we construct them explicitly because we actually have to use this formula for a different problem. But if you just think about the sphere packing problem, so it already tells you something, and this gives a unique candidate for well, SP magic function. And that candidate, so if you just remember the discussion on this board, all of these values would vanish for this magic function, which would basically leave you this, this one, the B1. So i.e., this candidate is actually one of these functions appearing in the formula, maybe up to rescaling. So, are there any questions so far? Yes.
Yes, there's a question, Keith.
Yes, please.
Does this hold especially the dimension 8, or does it generalize to other dimensions?
This result generalizes to other dimensions. And in fact, there's some amount of flexibility that you can do. But, so you can shift the two ends inside the square root by some number. And that still works. And so what happens is in other dimensions, you might have to adjust this number. So the summation will start not from 1 to infinity, but from something else. And of course, all of the functions will have to be changed. But for every dimension, there is an interpolation formula like that. And up to finite dimensional choices, they're unique. And it hasn't been written down anywhere except in dimensions 8 and 24 and in our paper with these courses. So, so it's more a question of actually writing down all the details. The proof, it should go through automatically, so we just never worked out the general formula for arbitrary dimensions.
How stable is the square root of the integers? Can I perturb that?
Yeah, well, I think you can perturb it, but the perturbation is not like up to constants, but it's something small with n. So if your perturbation is sufficiently small as n goes to infinity, that's all right. And there is a paper actually that does it. So by João Ramos and Mateus Sousa. So one can perturb it. Perturbations are possible, but are kind of very small. So in principle, if you zoom out, you don't really see them. So, and so that's kind of leading to the actual topic of my talk.
So this gives a candidate for sphere packing in every dimension?
No, the problem is this formula is kind of a different story. It's somehow, for some reason, in dimensions 8 and 24, this story correlates with the story about sphere packing. So if you actually try to find the best function for other dimensions, you don't have these vanishing conditions at square root of even integers, because you don't have a lattice which is kind of tight for that bound. But what happens is actually you find these vanishing at other points which we cannot describe, and they're roughly like that, maybe with some deformation. But for those points, we don't have any results like this. So it's kind of a double coincidence. So only in the cases where this could be tight, we have a result which actually gives an explicit construction. And in the cases where it's not tight, so we care less about those, we actually can't solve this analytic problem, which is kind of, well, it's very annoying, but that's what's like this.
What about dimension 2?
So dimension 2 is bad for other reasons. So here I said these conditions actually hold for all integers n starting from 1. If you do two-dimensional lattices, they have a lot fewer vectors, actually, vector lengths appearing. And in fact, if you count the density among integers, it's 0. So here it's positive density, it's exactly every even integer appears. In the case of two-dimensional lattices, it's density 0. And in fact, we have now several different proofs of the fact that, I mean, if you replace these numbers by the lengths of lattice A2, for example, there's no such formula, and you shouldn't even expect it. So it has the wrong properties. And so it kind of suggests that in dimension 2, there will be no uniqueness for magic functions, even if they exist. And we kind of believe that they will. Okay, so let me move to, well, the general question. So we have this somewhat complicated result. And I should say, so I will not talk about the method of proof at all. But what's surprising, it looks like an analytic statement in Fourier analysis, but actually the proof is a lot more like an arithmetic statement, and the way we construct all of these functions, so it involves using modular forms, which a priori you wouldn't really expect just from this formulation, even that they're relevant. Okay, so here's a question. So I kind of outlined here, so we have some data for the function, and then from that data, which is kind of discrete, so we have two discrete sequences, one on the function side and the other on the Fourier side. We reconstruct the function completely in a perfect way. And in fact, so this formula, it's, like I said, it's kind of tight in the sense that if you throw out just one number from the sequences anywhere, it will not work anymore. And actually, the function that verifies this failure is one of these functions appearing in the formula itself. So if you look at the values of Bn at all of the other points, it's actually like a delta function at that chosen node. So, but let's forget about several things. So I had functions in higher dimensional space. They were radial. Also have derivatives. So let's just simplify the problem a lot. So I'll mostly talk now about one-dimensional case. So let's say I have two closed subsets. And V will be some space of functions which for the most of the examples you can think of them as Schwarz class. But really, just to formulate the question, I want it to be closed under Fourier transform and maybe have contained in continuous functions, maybe decaying at infinity. So that's kind of the minimal set of assumptions you need to even ask the questions. So given two subsets of the real line and the space of nice functions, which I'll usually just ignore, it will be clear what the space is. When do the restrictions determine the function? Or in other words, equivalently, if f restricted to a is 0 and the Fourier transform restricted to b is 0, when can we conclude that the function itself must vanish? And so this is a general question in Fourier analysis, which one could have asked it 100 years ago. And in principle, there are some results in harmonic analysis which are really close, and some which are exactly this question, but in different form. But somehow, if you look for an example of such sets, A and B, with this property where A and B are both discrete sets, you wouldn't find anything beyond probably the last 10 years. So this is a general question. And so let's say if the pair AB has this property, well, we'll call it a uniqueness pair. Or I'll probably abbreviate it to UP. Hopefully it doesn't clash with any of the other contractions we had before. And in fact, to be completely honest, I would have to include the space of functions in the definition, but I will usually be quite sloppy about that. So I'll just talk about uniqueness pairs like that. And so there are some examples, and basically the rest of the talk will be me discussing 4 examples of this phenomenon. And the fourth one is the title, essentially. But the first example is classical, and it's not balanced in the sense that one of the sets is much bigger than the other. So the classical situation is you take either of the two sets, like let's say A, to be the complement of a finite interval, let's say between -1/2 and 1/2, and you take B to be the set of integers. Well, the claim is that this is a uniqueness pair. And depending on your tastes, you would attribute some names like Pelly-Wiener, or maybe Kotelnikov-Whittaker-Shannon, or maybe some other, to this phenomenon. And so here, basically, if you look at the two conditions, so one of them is telling you that your function is compactly supported, and the other is giving you sampling at equally spaced points. But actually, there's a way to write down an explicit formula without even thinking. And I already wrote this formula. Well, I'll write it in different notation. I already wrote it when I was proving von Elkis bound. So you write the Poisson summation formula. And if you look at both sides of this equation, well, if you rewrite it where you pick one term, keep it on the left-hand side, and then you put everything else on the right. Well, this is your kind of interpolation formula. So this is the proof. If you pick your V to be in the interval that's missing, you reconstruct everything else in this formula is known on the right-hand side.
When you say determine, you don't mean to reconstruct, but just asking the question of.
Yeah, well, okay, so I asked actually a weaker question, but whenever you have an actual reconstruction formula, it gives you the answer automatically. Yeah, I could just try to prove it by different means, but in this case, I want to write a formula, and in fact, I'll quickly give an example where essentially the only way of proving such a result is by giving a formula, which is a bit strange. So this is kind of a classical example, and then there's well, some names. But these are not exactly this type of setup, but equivalent setups, so Pelly-Wiener, etc. I'm sure there are other people I'm forgetting. And if you actually restrict to the class of functions which vanishes on A, you can rewrite it as a more classically looking sampling formula where you just have either band-limited functions and then you reconstruct from values at integers or something similar. Okay, so that was the first example. The next example actually is, in a sense, much easier. And that's probably the only example where you can work everything out, well, to some extent. So let's, instead of looking at the real line, look at the discrete Fourier transform. So it doesn't matter too much how you normalize it. Whichever way you like will work. So in this setting, one can ask a completely equivalent question, except now we don't even have to bother, worry about closedness or anything like that. So we just ask a question when f can vanish on B and on A, and then Fourier transform can vanish on B. And in this case, this is a finite dimensional question, so at least something we get for free from linear algebra, which is that A, the size of A plus the size of B should be at least n. And this doesn't require knowing anything even about the Fourier transform, so that's completely free. In general, there's no hope for this to be a kind of a sufficient condition, because one can have examples. For example, if there is a subgroup and we take f to be the indicator function of the subgroup, that would be kind of a counterexample. But what happens if there are no subgroups, which is the case for prime order of the cyclic group? And this is a very nice result by Perry. So theorem. And I'll formulate it the way actually it's stated in the paper, but you'll see in a second that it's equivalent. If M is prime, F on the cyclic group is non-zero, this implies that the support of f, the size of the support of f, plus the size of the support of the Fourier transform of f must be at least, must add up to at least n plus 1. And if you think about this, this is exactly the condition that I need for the pair of sets to be uniqueness pair. So it tells you that, as a reformulation, the condition A plus B bigger than or equal to n is also sufficient. If n is prime. And that's probably, well, one can't hope for a better answer than in this case. So even if you ask this question for non-prime cyclic groups, it already becomes a lot more complicated. So this is probably the best one can hope for. Okay. So this was the second example, and the third example. So to motivate this whole discussion, I started with a complicated formula in 8-dimensional space, which involved various values of the Fourier transform of x derivative. And so there is a kind of a toy model, if you wish. Maybe it's not exactly a toy model, it's still not so trivial. So if we take, okay, so here I want to actually come back to mentioning the space of functions. So let V be the space of Schwartz functions, which are even. And then A and B will be almost equal. So let me define A first. This will be just square roots of all non-negative integers, and B will be A minus the origin. And the claim is that this is a UP. And in fact, this is the first case where actually proving that this is a uniqueness pair directly, we don't really have any proof that does it. But what we do have is an explicit formula that does a reconstruction. And that's somehow, it's very counterintuitive, but this is, it's kind of the starting point of the whole story. So I think from 2017, there is a formula. So for any f and v, one can explicitly reconstruct much like in the case that I started with, coming from the sphere packing problem. One can explicitly reconstruct the function from the data at square roots of integers, but now we don't need to use any of the derivatives and anything else. And again, this is completely explicit, and it's essentially unique, except here I choose usually to have symmetric summation on both sides. And this is slightly redundant because there's a Poisson summation formula which tells you there's one relation between these values that also always holds, which is the sum over integers. Oops. Which means that you can throw out one of the squares from the summation somewhere here. Whichever is one you like, you can remove it. But in this way, it's somehow nicer because then actually the coefficients are Fourier transforms of each other. And again, the proof kind of, even though it looks like a result in purely analytic result, the proof has more to do with modular forms than with harmonic analysis. And so, but that was very puzzling because we asked several people who work in harmonic analysis whether they have seen any results like that before. In fact, not the interpolation formula itself, but the fact that it's a uniqueness pair. And to the best of our knowledge, it was not known, but people got interested. And so there's kind of several results now which are of analytic nature, which we don't have any explicit formulas for, but they're kind of a lot more flexible. And so I want to state some results, but then I want to also talk about Riemann zeta a little bit. So one can ask a more general question. Let's take, well, just sequences given by powers of n. Maybe I'll keep both signs. For some constants c and d which are positive, and some alpha and beta which are positive. And now the question is, can we decide which of these are uniqueness pairs and which are not? And so this was kind of attacked by two groups of people. So first there was a nice paper by the same people I talked about before, by João Ramos and Mateus Sousa. They actually managed to prove by purely analytic means. So for example, if alpha plus beta is less than 1 over square root 2, then AD is always a uniqueness pair. In fact, they gave a little bit more precise region, but in a second it will be kind of irrelevant. So they proved something, in terms of the parameters alpha and beta, they proved something like in this region there's always uniqueness. And this has, I mean, you can completely forget about the constants C and D, they play no role. Well, if you look at this result, this is what we had. This is what actually started the story. We had alpha equals beta equals 1/2, and C equals D equals 1. But in fact, there's some obvious rescaling one can do, so one only has to worry about the product of C and D. So this is a uniqueness pair. And there is a heuristic which unfortunately I don't have any time to explore. There is actually a heuristic for what the sizes of A and B should be for one to even hope for a result like a uniqueness. And it's roughly related to what people in signal analysis call the 4WT theorem. So if you've ever heard these words, that will tell you a lot. If you haven't, probably that won't tell you much. But so roughly one should have if you intersect A with an interval between -x and x, and then you add to it the number of points in the B in the interval from -y to y, this should roughly be at least for, actually maybe if I use the classical notation of W and T, this should be at least for WT, maybe minus some log terms, and so on. And so this is essentially something called the Legendre transform. So if you have the counting function for one set, the complementary set should have at least as many points as the Legendre transform. as kind of more general and longer story, but if you apply this kind of idea to these sets, you have a good idea that anything below the diagonal alpha plus beta equals 1 should work, should be a uniqueness pair. And anything above that should not work. And that was, in a very precise way, resolved quite recently. So there's a paper by, well, I'll do it not in alphabetic order, but Nazarov, Sodin, and Surikov. So they proved almost everything in this setting, namely if alpha plus beta is bigger than 1, then one never gets uniqueness pairs, which means, in fact, there's infinite dimensional spaces of functions which vanish on both sides. If alpha plus beta is strictly less than 1, then one always gets uniqueness pairs. And kind of interestingly, in the critical case, when alpha plus beta is 1, which this result was about, there is again some splitting, so there is a very sharp transition between uniqueness pairs and non-uniqueness pairs. And basically, if CD is bigger than constant, well, whatever it is, and if CD is less than this constant, then one gets not uniqueness pairs and uniqueness pairs respectively. And their method, unfortunately, doesn't tell anything in the critical case, which is what this whole story started with. So there's exactly one point for all of these parameters where you don't know the answer, and it's kind of dramatic. So you don't know even, we don't really have even a good idea what the answer should be. And so finally I can get to the title, and hopefully.
Sorry, the case CD equals 1 is not covered here, right?
Yeah, it's not. So this result doesn't follow from the analytic techniques.
This is a positive. Yeah, so this is an example. It's positive. It could be negative in general.
Yeah, we don't know. But it's kind of the whole story started from yes.
Is it because of density and rigidity reasons, like sort of?
Yeah. So. Well, they need some kind of epsilon of room for their argument, and that's a requirement. If you're exactly in this rigid case, it doesn't work at all. And the problem is also our argument by itself is extremely rigid, so we can't deform that, and there is no hope. And so it's kind of none of the techniques we have are applicable in the case where alpha and beta are not 1/2.
So the analytic techniques are not reconstruction techniques.
No, this is completely non-construct. I mean, okay, it's to an extent they also get some interpolation formulas, but again, not by constructing them, but by proving that they exist. So, but these are all existential results, except for the one that we started with. So we have actually very limited supply of kind of these tight cases, and so almost no tight uniqueness pairs are known. And so what is so tight just means that you can't throw out any of the information you're given. So if your sets A and B are minimal possible. If you remove at least one point, you fail. And so basically we have this result. We have the result coming from the sphere packing problem, which is, I mean, it's not even directly in the same setting that I'm talking about, but it's kind of like it. We have a few results which are a little bit more general than these, but that's about it. And then there's the result that I want to talk about, which is, I mean, given our absence of constructions, it's kind of ridiculous that we have this, but nothing simpler. So this is a theorem by Bondarenko, myself, and Christian Seip. Andrei Bondarenko, and Christian Seip, and myself. So I'll formulate it in very brief terms first, and then I'll say a little bit more. So if you take A to be, well, the set of a gamma such that zeta of 1/2 plus I gamma is 0, and I want to pick it in, okay, so, sorry. So I want to pick only the non-trivial ones. Hopefully it's legible. And the zeta, well, the way I write it is probably, so we take all of the non-trivial zeros of zeta function, and then we pretend that the Riemann hypothesis is true and rotate them to lie on the real line. And that would be the set A. And as the set B, we take plus minus logarithms of all integers divided by 4 pi. And there's a more precise statement, but one of the corollaries of this theorem that we proved is that this is a uniqueness pair, and it's also tight. And there are two comments that I want to make. Maybe.
Take your time.
Should I? Well, how much time am I allowed to take?
I don't understand. I mean, gamma, and then you have the imaginary part of gamma.
Yeah.
Yeah, okay, so.
Is gamma between minus.
Gamma is real, or?
Gamma is
Well, if you assume RH, yes. If you assume RH, yes.
So assuming RH is just writing this gamma is real.
Yes, yes, yes. Yeah, so, okay, let's assume RH. RH and multiplicity 1. Which, I mean, I'm sure many people are not comfortable with assuming either, but that's what you have to do. That's what you have to do if you want this to fit actually the setup I started with.
I don't know, it's okay. You can erase it.
And then you don't need this, you just take, well, you still need to say that you don't want the trivial ones. Yeah, it's maybe not the common way to normalize it, but hopefully that works. So this is a uniqueness pair, it is tight, and actually it's tight, everything works even if you don't assume multiplicity 1 conjecture and RH, except that you have to modify the definition. So you'll have higher derivatives at points which have multiplicity greater than 1, and then some of these points are not on the real line, maybe. But even if it fails, the statement about uniqueness pair is correct. And the proof is completely constructive, well, except, so we actually give an interpolation formula. But it's kind of explicit in the same way as zeros of the zeta function are explicit. So if you give all the zeros, then I can write down a formula, but otherwise, I mean, it depends on the properties of those. I'll finish in a second.
You're sure?
Sorry, is there a question?
I'm trying to understand. So the zeros, you take the zeros with the imaginary part.
Yeah, okay, so
even when it's previous.
should I write it the proper way? So it's
The set is the real part.
so you kind of shift it by a half and then rotate it.
It's imaginary parts of the...
Yes, yes, yes. Well, I mean, they're imaginary if you believe RH. If you don't believe, there's some. Yeah. But it's exactly this set. So
doubly imaginary if you don't believe.
well, no, but what's interesting, kind of, I gave you this 4WT theorem, which gives you a heuristic for when one can expect any such formula to hold. And this is actually like a tight case of this formula, so it's very precise. Any of these numbers you throw out, you lose the uniqueness property. And it tells you something about zeros, which one can undoubtedly prove a lot easier. So it tells you essentially the number of zeros up to a certain imaginary part, maybe without any good error term, but by a completely different method. So this has nothing to do with arithmetic of primes or anything or explicit formulas. And the statement is kind of orthogonal to any arithmetic properties of the zeta function we could find. Except, I mean, if you combine it with the explicit formula, it gives a lot of identities for the. So there's an explicit formula, explicit interpolation formula, which we have, and it looks. So in a suitable space of analytic functions, one can reconstruct anything from values at zeros. But possibly with, well, if there are some multiplicities, you also have to add derivatives. Plus the sum over all logarithms of integers. Maybe, I mean, I'll just, let's just take f as even, but that's not terribly important, so you just take half of them. So, times un of s. So there is a formula where actually everything written here is explicit. These are completely explicit functions, they don't depend on anything. But these functions are essentially constructed using the zeta function itself. So it depends on how it behaves at the zeros, at the corresponding zero. But, I mean, modulo that, it's completely explicit. So there's part of the recipe which comes from something that has nothing to do with zeta function, and part of the recipe which exactly comes from it. And so if you combine this with explicit formula, Riemann veil, you get some strange identities for these functions, which we cannot prove in any other way other than by combining the two facts together. And also the fact that this is a uniqueness pair. Again, we don't have any analytic way of proving this. So we don't have, it's only because we have an explicit formula, we get this as a corollary, but otherwise it looks a little bit inaccessible. And maybe let me stop here.